So this is called a buffered solution. Okay, a buffered solution. And a buffered solution has a weak acid plus its conjugate base in high concentrations. And what that does, the whole point of a buffered solution is that they resist a change in pH. Okay, so to prove that, we're going to take 1 liter of those two solutions, plus we're also going to do 1 liter of just water. And we're going to add enough solid sodium hydroxide to make a 0.05 molar solution of sodium hydroxide. Okay, so let's just start with a simple one. Let's say that we have 1 liter of water. Okay, and so to 1 liter of water, I'm going to add 0.05, enough sodium hydroxide to make a 0.05 molar sodium hydroxide solution. So if I have sodium hydroxide and I add it to water, that makes sodium ion plus hydroxide ion. So if this starts out as 0.05 molar, it'll make 0.05 molar hydroxide ion because sodium hydroxide is a strong base. It dissociates completely. Okay, so the pH of a 0.05 molar sodium hydroxide solution is going to be, well, we can find that we know the pOH is going to be negative log concentration of OH minus. And we know that pH is going to be pH plus pOH equals 14. So 14 minus pH equals 14 minus pOH, which is 14 minus the negative log of concentration of OH minus. Okay, so when I plug my number in, I get 12.7. So if I have 1 liter, if my solution is water, okay, neutral, if I look at the change of pH of water, okay, pure water has a pH of 7. So our final pH is 12.7, and that's going to go to a pH of, our final pH is 12.7, our initial pH is 7, so our change in pH is 5.7. That's a big change, right? Keep in mind that this is a log scale, so this is almost 6 orders of magnitude, or 1,000,000 times change in concentration of hydronium ion in the solution. So that's a big change. Okay, so let's look at what happens if I add this to the acid. Okay, so here's what happens if we add to pure water. Now I'm going to add this sodium hydroxide to the acid. Okay, so my acid in solution, I have HF, I have water, obviously, I have fluoride ion, I have sodium ion, oops, not a plus here, I have hydroxide ion. Why do I keep putting pluses here? Hydroxide ion, and then I also have hydronium ion. So I'm getting this from, if we go way back up here, right, we look at our equilibrium. Here is what is present at equilibrium if you have just a solution of hydrofluoric acid. So there's what we have, and then we add sodium hydroxide to it, and sodium hydroxide dissociates completely into sodium ion hydroxide ion. Okay, so I have hydroxide ion, which is a very strong base. Okay, and that hydroxide ion is going to react with the HF in solution. Okay, so I'm going to assume 1 liter of solution just to make my calculations a little easier. And I'm going to do something called a Rice end. So this is like this is doing stoichiometry in a table. And so in a Rice end table, your values need to be in moles, not molarity. Okay, but I'm making this easy on myself because I have 1 liter of solution. Okay, so I had what's going to happen is that the hydroxide ion is going to react fully. It's not going to be in equilibrium. It's going to react fully to make fluoride ion plus water. Okay, because this is super strong. So this wants to accept a proton, and it sees the hydrofluoric acid, which though not a great proton donor, is good enough. Okay? So our initial amount of each thing, our initial amount of HF is going to be, so molarity equals moles solute per liter solution. So if I want to know the moles of solute, that's going to be molarity times liters solution. Okay, now this one's easy because my molarity was 1.0 molar and my liters of solution is 1 liter. So I just end up with 1 mole of HF. Okay, and by the same rationale, hydroxide ion will have 0.05 moles at the beginning. Okay, now I can see from this that my hydroxide ion is going to be the limiting reactant. So this is going to decrease, it's going to fully react, and then these two will go, or the fluoride ion will increase by a little bit. Okay, so now I have 0.95 moles of HF and 0.05 moles of fluoride ion at the end of this reaction, and no more hydroxide. Remember, this isn't an equilibrium. This goes to completion. So this is just straight stoichiometry. I use a Rice end table versus a Rice equilibrium table. But now, these ending concentrations here give us these ending amounts give us our initial concentrations to redo our equilibrium calculation. So I can do a Rice EQ table, right, equilibrium table, where we start out, here's our equilibrium that we care about. Okay, and just like we saw before, this is going to have a concentration of 0.95. Now we're going to go back to concentrations. So I'm going to take my moles of solute and divide it by my liters of solution, which again I've made very easy because everything's like ones. Okay? And then my hydroxide ion concentration is going to be, um, sorry, not hydroxide ion, my fluoride ion concentration is going to be 0.05 molar. And my initial concentration of hydronium ion is H3O plus because that's what we're trying to find. So now my change here is going to be minus x, so I'm going to make that 0.95. Now this is plus x, so x, and this one needs to be 0.05 plus x. And I can't make the assumption there, okay? So this is going to lead to us solving a quadratic. I'm just going to solve this kind of quickly. I'll move the video ahead at a slightly faster speed so you can get to the end here. Okay, so there's our equilibrium concentration for the hydronium ion, and we can get the pH of that, 1.95. So let's take a look at the change in pH for our acid solution. So our water solution had a change in pH of 5.7. Okay, our acid solution, we went up to 1.95 from our starting pH of 1.57. You see that up here? Okay, our starting pH of 1.57. So that equals 0.38. Now that's a big, big change. So already, just by having a weak acid in there, you make a big difference in your ability to absorb base without a major change in pH. Okay, so let's take a look at the buffer solution this time, the buffered solution this time. Okay, so now in our buffered solution, we have all the same things that we had before. So here's our things in solution. Okay, so once again, the hydroxide ion is going to react with the HF. Okay, so our first step is going to be to do stoichiometry. Okay, so that's rice with moles. And this gets us our starting concentrations for equilibrium. Then we're going to get initial concentrations of everything. We'll find equilibrium conditions. And we're going to do that using a rice table. And then we'll determine pH. So it's exactly like we did before. This is just kind of the setup that we're going to use. So if you're feeling confident, you could give this a try and see if you can figure out what values go where. And then, if you get stuck somewhere, kind of look at where I am, and then see if you can finish this problem out without any support. Okay, so my first thing is I'm going to do a rice end. Okay, so this is the hydrofluoric acid, the weak acid, reacting with that strong base, that hydroxide ion. and that's going to make fluoride ion plus water. All right. Now, our initial amounts are 1 mole of the hydrofluoric acid. Okay, so remember this is a 1 molar hydrofluoric acid solution. And we also added 1 molar sodium fluoride. So we start with 1 mole sodium fluoride, okay, which is just 1 mole of fluoride ions because it dissociates completely. And we also start with 0.05 moles hydroxide ion. Hydroxide ion is clearly our limiting reactant, so that will get fully used up. Okay, now the difference here is that fluoride ion is going to end with a bunch, right? We're still going to end with a bunch of fluoride ion. Now, these are the amount of moles, this is in moles, and I can turn those into concentrations by dividing them by the volume, which in this case is 1 liter. So those numbers will be equal. So now I can set up my RICE-EQ, and we're still doing exactly the same equilibrium that we've been doing the whole time. Okay, my initial concentration of HF is 0.95. My initial concentration of hydronium is 0, and my initial concentration of fluoride ion is 1.05 molar. We're going to go down by x, and we're going to make our assumption that that's 0.95. That's going to go up by x, and then this one is going to go up by x, but now we can make the assumption that that's just 1.05. 1.05 plus x is just 1.05. Now I can do my calculations and figure out the pH. Okay, I'll use that to get hydronium ion concentrations, and I'll get a pH is 3.19. Okay, I'm skipping a few steps there, but you should be pretty confident with this at this point. Okay, so now for this one, my change in pH is going to be the new pH, which was 3.19, minus the pH of the buffered solution, which was 3.14. Look at that. Okay, 0.05. So the other ones were 0.38 if I just had the weak acid, and then 5.7 if I have no weak acid in there. Okay, this is how buffered solutions work. All right, and you're just going to be going through a lot of for tonight, you're going to be going through a lot of determine the pH of this buffered solution, determine the pH if you add a little bit a little bit of acid or a little bit of base to the buffered solution. Okay, that's our goal for today, is to be able to understand the mathematics of how the buffer solution works and do some calculations. The last thing that we need to know today is something that we probably should have covered before, but we didn't. So if I have the equilibrium HA plus H2O yields H3O plus A minus, I can also do that A minus can act as a base, making OH minus plus HA. Now the Ka so the equilibrium expression for the first one is Ka equals concentration of hydronium times concentration of the anion over the concentration of the weak acid HA. I can also do the equilibrium expression for the second one, but instead of Ka, this is going to be Kb. Kb equals concentration of hydroxide ion times the concentration of the weak acid over the concentration of the anion. Now, what happens if I take these two things and I multiply them? So I get Ka times Kb equals concentration of hydronium ion times A minus times concentration of hydroxide ion times concentration of HA all over concentration of HA times concentration of A minus. Okay? And when I look at this, I'm like, hey, wait, a bunch of stuff cancels out, like the anion and the concentration of weak acid. So all I'm left with is Ka times Kb equals concentration of H3O plus times concentration of OH minus. And remember that concentration of hydronium ion times the concentration of hydroxide ion is just Kw. So Kw equals Ka times Kb. You will need that to do some of these problems.